Imagine this. At the height of World War II, Axis sailors openly mocked American radar, calling it practically useless. Why? What critical piece were they missing? They thought they had the edge at sea, laughing at early American technology. But a secret weapon was about to change everything, and they never saw it coming. In the deadliest naval battles, seeing the enemy first meant survival. So why did America's foes think our ships' electronic eyes were blind? It's easy now, looking back across the decades, to think of World War II as a foregone conclusion, a time when American might inevitably rose to meet the challenge. We remember the industrial power, the sheer number of ships, planes, and brave men sent into the fray. But history is rarely so simple, is it? In the dark early days of the war, particularly on the vast and unforgiving oceans, the fight was balanced on a knife's edge. And a crucial part of that balance, one often overlooked in the grand narratives of battles won and lost, was technology. Specifically, the ability to see the enemy before they saw you, even in pitch darkness or thick fog. That's where radar came in. Yet, there's a fascinating, almost unbelievable footnote to this story. For a significant period, our enemies, particularly the Axis powers of Germany and Japan, looked at early American naval radar systems and, well, they scoffed. They mocked them. Some reports even suggest they considered them largely useless toys, certainly not the decisive tool they would eventually become. Now, why on earth would they do that? Weren't they facing the same dangers, the same need to detect threats from afar? It seems almost suicidal in retrospect, doesn't it? But their confidence, their dismissal, wasn't born entirely of ignorance or arrogance, though there might have been a bit of that too. It stemmed from a fundamental difference in the kind of radar technology being used, a difference measured in mere centimeters on the electromagnetic spectrum, but one that translated into miles of tactical advantage or disadvantage at sea. They believed they understood radar, and by their understanding, the American systems just didn't measure up. They were missing a key ingredient, a revolutionary breakthrough that was brewing just over the horizon, something called centimetric waves. This is the story of why the Axis powers underestimated American radar, the very real limitations our sailors faced because of it, and how a tiny, almost magical device generating incredibly short radio waves would ultimately silence the mockery and help turn the tide of the war at sea. It's a tale of science, secrecy, desperation, and the kind of quiet ingenuity that often proves more powerful than the loudest boasts. Think about being on watch, staring into the blackness of the North Atlantic or the Pacific night. The only thing between you and disaster might be a faint blip on the glowing screen. Now imagine knowing the enemy might have something better, or worse, believing your own gear isn't quite up to snuff, even while your adversaries think it's a joke. That was the reality for many early in the war. So let's peel back the layers of this technological duel. Before we dive deep into the waves and the wires, it helps to understand where everyone stood when the war clouds gathered. Radar, this idea of using radio waves to detect objects, wasn't exactly a brand new concept sprung out of nowhere in 1939. Researchers in several countries, including the US, Britain, Germany, France, Italy, Japan, and the Soviet Union, had been tinkering with the basic principles since the early 20th century. Heinrich Hertz himself had shown back in the 1880s that radio waves reflected off metallic objects. But turning that laboratory curiosity into a practical, reliable military tool, that was a whole different kettle of fish. By the mid-1930s, the growing threat of air power, particularly long-range bombers, spurred serious investment. The British, famously, were pouring resources into their Chain Home system, giant towers along their coast designed to give early warning of approaching German aircraft. This was a monumental effort and absolutely vital for the Battle of Britain later on. But notice, Chain Home was land-based, designed to look up and out over the water. Putting effective radar onto a moving, pitching, rolling ship and making it reliable enough for sailors to depend on presented a host of new challenges. Size, weight, power requirements, stabilization, interpreting the signals amidst the clutter of waves. It was tough. The Americans, buffered by two oceans, were perhaps a bit slower off the mark than the British or Germans in deploying widespread radar, especially for naval use. Early efforts in the U.S. Navy began in the mid-1930s at the Naval Research Laboratory. They experimented with various frequencies, trying to find the sweet spot between range, resolution, and antenna size. Their initial successes, like the experimental XAF radar tested in 1938, operated on frequencies around 200 megahertz. Now, 200 megahertz might sound like a big number, but in radio terms, it corresponds to a wavelength of about 1.5 meters. Remember that number, meter waves. These relatively long waves required large antennas, often looking like big bed springs or mattress arrays, which were cumbersome to mount on ships and difficult to rotate quickly. More importantly, these longer waves had trouble detecting smaller targets like surfaced submarines or low-flying aircraft, and their resolution wasn't great. Imagine trying to read fine print with blurry vision. That was kind of the problem. You could see something big was out there maybe, but distinguishing details or picking out smaller threats was hard. This led to the first operational U.S. naval radar, the CXAM, deployed starting in 1940. It was a step, a crucial one, but it operated in that same meter wave range, around 1.5 meters, inheriting those limitations. Early versions could spot aircraft fairly well at a distance and maybe a large warship, but their performance against smaller targets or in distinguishing ships within a formation was lacking. If stories like this about the hidden battles of technology in the war fascinate you, consider subscribing so you don't miss our next deep dive into the innovations that really made a difference.
Now, contrast this with the Axis powers. The Germans, through companies like Gemma and Telefunken, had also been hard at work. Their early naval radar, known as CTACT, which began operational testing even before the war, also started in the meter wave range, typically around 80 centimeters, around 375 megahertz. It was decent for its time, capable of detecting large ships and providing ranging information for gunnery. The Kriegsmarine fitted it to many of their capital ships. However, they too faced limitations with resolution and detecting smaller targets. The Japanese Navy was perhaps even further behind initially in radar development compared to the Germans or the Allies, focusing more on optics and night fighting techniques, which they excelled at early in the war. Their initial radar sets, deployed in the early 1940s, were also meter wave systems, often bulky and sometimes unreliable, derived partly from captured British or American equipment or based on German designs. So, on the surface, it might seem like everyone was struggling with similar problems in those early years. Meter wave radar was the established technology. It had its uses for long-range air warning and detecting large surface contacts. But it wasn't the pinpoint accurate, all-seeing eye we associate with radar today. Why then the Axis mockery specifically directed at the U.S. systems? Part of it likely came down to operational experience and doctrine. The Germans, involved in the Battle of the Atlantic from day one, gained rapid, brutal experience in naval warfare, including the use and limitations of their CTACT radar. They knew what it could and couldn't do. They might have observed early American radar performing similarly, or perhaps even less reliably in some encounters, and concluded, somewhat reasonably based on their own meter wave experience, that it wasn't a game changer. They might have thought, okay, they have radar, we have radar. It helps a bit, but skill, gunnery, and surprise still rule the waves. They focused on improving their existing meter wave systems and developing passive detection gear like radio direction finders and hydrophones. The Japanese, relying heavily on their superior optics, night training, and the formidable long lance torpedo, initially didn't feel a pressing need for advanced radar, perhaps underestimating its potential impact, especially in adverse weather or at night when optics were useless. Their early victories in the Pacific seemed to validate this approach. So, when they encountered American ships equipped with early sets like the CXAM or the SC, another meter wave air search radar, they compared it to their own experiences and perhaps intelligence reports on German systems and found it wanting. It didn't provide the sharp, clear picture needed to target individual ships accurately in the dark, nor could it reliably pick up small, fast-moving threats like PT boats or low-flying torpedo bombers until they were dangerously close. From their perspective, shaped by their own technological path and operational doctrine, the American radar they were seeing simply wasn't the revolutionary weapon it was sometimes claimed to be. It was useful, sure, but not something to fundamentally alter the balance of power. It was dismissible. And that brings us to the heart of the matter, the fundamental physics that made their assessment seem logical at the time and why it was ultimately so wrong. We need to talk about wavelengths. Understanding why those centimeters made such a world of difference requires a little detour into how radar actually works. But don't worry, we'll keep it straightforward. Imagine shouting in a big, empty room. Your voice travels out, hits a wall, and an echo comes back. By timing how long it takes for the echo to return, you can get a rough idea of how far away the wall is. Radar does essentially the same thing, but instead of sound waves, it uses radio waves, and instead of walls, it looks for ships, planes, or even periscopes. A radar set sends out a pulse of radio energy from its antenna. If this pulse hits an object, some of that energy bounces back towards the antenna, which now acts as a receiver. The radar measures the time it takes for the pulse to go out and come back, and since radio waves travel at the speed of light, a known constant, it can calculate the distance to the object very accurately. That's the ranging part. By using a directional antenna, sweeping it around, the radar can also tell the direction, or bearing to the target. Put range and bearing together, and you know where the target is. Simple enough, right? But here's where the wavelength, the physical distance between the crests of those radio waves, becomes absolutely critical. Early radars, like the American CXAM and the German CTACT, operated with wavelengths measured in meters or tens of centimeters, like CTACT's 80 centimeters. Think of these as big, broad waves. Now, for a radar wave to bounce back effectively, the object it hits needs to be at least roughly comparable in size to the wavelength, or ideally larger. Big targets like battleships or high-flying bomber formations reflected these meter waves reasonably well, allowing for detection at significant distances. That was their strength, long-range early warning against large threats. But what about smaller targets? A surfaced U-boat conning tower, the periscope of a submerged submarine, a low-flying aircraft skimming the waves, or even trying to distinguish between two destroyers sailing close together in a formation. Here, the large meter waves struggled. It's like trying to feel the shape of small pebbles using only your palm. You know something's there, but the details are lost. A wave that's 1.5 meters long just doesn't see a small periscope tube very well. Much of the energy just flows around it, and the reflection that comes back is weak, easily lost in the background noise, or sea clutter, the unwanted radar reflections from the waves themselves. Furthermore, the resolution of a radar system, its ability to distinguish between two closely spaced targets, or to show the precise shape of a single target, is directly tied to the wavelength and the size of the antenna. To get a narrow, focused beam, which means better resolution and accuracy, you either need a very large antenna or a much shorter wavelength. With meter waves, achieving a truly sharp beam required antennas that were impractical for shipboard use. The antennas for CXAM were massive, limiting how fast they could scan and making them vulnerable. The beams they produced were relatively wide, measured in degrees. This meant that two ships sailing close together might just appear as one large, indistinct blob on the screen. Trying to target a specific vessel within that blob for gunnery was often incredibly difficult, if not impossible based solely on the radar picture. Think about pointing a broad flashlight beam versus a sharp laser pointer. The flashlight illuminates a wide area, but you can't pinpoint a tiny detail. The laser hits exactly one spot. Meter wave radar was like the flashlight. What was desperately needed was the laser pointer. Access engineers knew this. They understood the physics. They knew that to get better resolution, detect smaller targets, and use smaller, more practical antennas, they needed to move to shorter wavelengths, down into the centimeter range. The Germans were experimenting with this, developing systems like the Berlin radar based on captured Allied technology later in the war, but their initial operational systems were stuck in the decimeter, tens of centimeters range at best. The Japanese were even further behind in developing microwave technology initially. So when they encountered American ships equipped with early radar, sets like the CXAM or the SC, another meter-wave air search radar, they compared it to their own experiences and perhaps intelligence reports on German systems and found it wanting. It didn't provide the sharp, clear picture needed to target individual ships accurately in the dark, nor could it reliably pick up small, fast-moving threats like PT boats or low-flying torpedo bombers until they were dangerously close. From their perspective, shaped by their own technological path and operational doctrine, the American radar they were seeing simply wasn't the revolutionary weapon it was sometimes claimed to be. It was useful, sure, but not something to fundamentally alter the balance of power. It was dismissible. And that brings us to the heart of the matter, the fundamental physics that made their assessment seem logical at the time and why it was ultimately so wrong. We need to talk about wavelength. Understanding why those centimeters made such a world of difference requires a little detour into how radar actually works. But don't worry, we'll keep it straightforward. Imagine shouting in a big, empty room. Your voice travels out, hits a wall, and an echo comes back. By timing how long it takes for the echo to return, you can get a rough idea of how far away the wall is. Radar does essentially the same thing, but instead of sound waves, it uses radio waves, and instead of walls, it looks for ships, planes, or even periscopes. A radar set sends out a pulse of radio energy from its antenna. If this pulse hits an object, some of that energy bounces back towards the antenna, which now acts as a receiver. The radar measures the time it takes for the pulse to go out and come back, and since radio waves travel at the speed of light, a known constant, it can calculate the distance to the object very accurately. That's the ranging part. By using a directional antenna, sweeping it around, the radar can also tell the direction, or bearing to the target. Put range and bearing together, and you know where the target is. Simple enough, right? But here's where the wavelength, the physical distance between the crests of those radio waves, becomes absolutely critical. Early radars, like the American CXAM and the German CTACT, operated with wavelengths measured in meters or tens of centimeters, like CTACT's 80 centimeters. Think of these as big, broad waves. Now, for a radar wave to bounce back effectively, the object it hits needs to be at least roughly comparable in size to the wavelength, or ideally larger. Big targets like battleships or high-flying bomber formations reflected these meter waves reasonably lightly well, allowing for detection at significant distances. That was their strength. Long-range, early warning against large threats. But what about smaller targets? A surfaced U-boat conning tower? The periscope of a submerged submarine? A low-flying aircraft skimming the waves? Or even trying to distinguish between two destroyers sailing close together in a formation? Here, the large meter waves struggled. It's like trying to feel the shape of small pebbles using only your palm. You know something's there, but the details are lost. A wave that's 1.5 meters long just doesn't see a small periscope tube very well. Much of the energy just flows around it, and the reflection that comes back is weak, easily lost in the background noise, or sea clutter, the unwanted radar reflections from the waves themselves. Furthermore, the resolution of a radar system, its ability to distinguish between two closely spaced targets, or to show the precise shape of a single target, is directly tied to the wavelength and the size of the antenna. To get a narrow, focused beam, which means better resolution and accuracy, you either need a very large antenna or a much shorter wavelength. With meter waves, achieving a truly sharp beam required antennas that were impractically huge for shipboard use. The antennas for CXAM were massive, limiting how fast they could scan and making them vulnerable. The beams they produced were relatively wide, measured in degrees. This meant that two ships sailing close together might just appear as one large, indistinct blob on the screen. Trying to target a specific vessel within that blob for gunfire was incredibly difficult, if not impossible, based solely on the radar picture. Think about pointing a broad flashlight beam versus a sharp laser pointer. The flashlight illuminates a wide area, but you can't pinpoint a tiny detail. The laser hits exactly one spot.
Meter wave radar was like the flashlight. What was desperately needed was the laser pointer. Axis engineers knew this. They understood the physics. They knew that to get better resolution, detect smaller targets, and use smaller, more practical antennas, they needed to move to shorter wavelengths, down into the centimeter range. The Germans were experimenting with this, developing systems like the Berlin radar, based on captured Allied technology later in the war. But their initial operational systems were stuck in the decimeter, tens of centimeters, range at best. The Japanese were even further behind in developing microwave technology initially. So when they observed American ships using radar that clearly operated in the meter wave spectrum, identifiable by the large antenna structures and the performance limitations they sometimes witnessed in battle or through intelligence, they likely drew a logical conclusion based on their own understanding. Their radar suffers from the same fundamental meter wave limitations as ours, perhaps even more so. It's not a decisive weapon. They focused on refining what they had, improving detection ranges for large targets, developing countermeasures like radar warning receivers, and relying on their other strengths. They mocked the American tech because, according to the known rules of radar as they understood them, it was limited. They were assessing it based on the current state of the art as they perceived it, unaware that a revolution was happening, hidden in plain sight, powered by a device no bigger than a hockey puck. That device, the cavity magnetron, and the centimeter waves it produced was the missing piece they couldn't fathom. So let's put ourselves in the shoes of an American sailor aboard a destroyer or cruiser in, say, 1941 or early 1942. Your ship is equipped with the latest radar the Navy has, perhaps the CXAM for surface and air search, or the SC air search radar. You've been told this is cutting-edge technology, your electronic eyes in the dark. But what was the actual experience like? Well, for detecting high-flying aircraft formations at long range, it was genuinely useful. The Battle of the Coral Sea in May 1942 saw some of the first extensive use of radar in a fleet action, and reports suggest the SC radars provided valuable early warnings of incoming Japanese airstrikes, allowing fighters to be scrambled. This was crucial. Being able to detect bombers 50 or 70 miles away gave the fleet precious minutes to prepare, minutes that could mean the difference between fending off an attack and suffering devastating losses. So for that primary role of long-range air warning, the meter wave sets earned their keep. However, the picture gets much murkier when dealing with surface targets or low-level threats. The resolution issues were a constant headache. The radar screen, a simple A-scope display in those early days, showed target range as a spike or blip along a horizontal line, with the height of the spike indicating signal strength. Bearing was read from a separate dial linked to the antenna's rotation. Trying to interpret these blips, especially when multiple targets were present or when sea clutter was high, required significant skill and often involved a degree of guesswork. Experienced operators could sometimes infer target size or type based on the blip's characteristics, but it was far from precise. Imagine trying to identify different types of vehicles miles away at night using only a flickering, blurry spotlight. It gives you a sense of the challenge. During night battles, like the chaotic series of engagements around Guadalcanal in late 1942, radar operators faced immense pressure. The early surface search sets, like the SC adapted for surface use, or the newer SG radar, which we'll get to, as it was the game changer, were still being deployed. Ships relying solely on older meter wave sets often struggled. Take the Battle of Savo Island in August 1942, a devastating defeat for the Allies. While failures in communication and readiness were major factors, the limitations of the available radar played a role. Allied cruisers, equipped primarily with SC air search radar, failed to detect the Japanese cruiser force in time, partly because the radar wasn't optimized for surface search, and operators may not have been fully proficient or trusting of the fuzzy contacts they might have seen amidst the land clutter from nearby islands. The Japanese, relying on skilled lookouts and superior night optics, achieved complete surprise. Even when contacts were made, interpreting them was hard. Was that one large ship or two smaller ones? Was that blip a destroyer making a torpedo run, or just a large wave? Gunnery solutions based purely on meter wave radar data were often inaccurate. The wide beam width meant the bearing information wasn't precise enough for pinpoint targeting, especially at longer ranges. Fire control often still relied on visual spotting, star shells, or searchlights, negating some of radar's key advantages. And then there was the U-boat menace in the Atlantic. A surfaced submarine presented a very small radar target. Meter wave radar, especially early airborne versions, ASV, struggled mightily to detect them, particularly in rough seas where sea clutter could easily mask the sub's return signal. A U-boat could often spot the searching aircraft visually before the aircraft's radar could detect the submarine, allowing it to dive and escape. This inability to reliably detect surfaced U-boats, especially at night, was a critical vulnerability that cost the Allies dearly in shipping losses during the early war years. The Battle of the Atlantic was, for a time, being lost, partly because existing radar couldn't effectively counter the U-boat threat in all conditions. Sailors knew this. They understood the tools they had were imperfect. While radar offered a capability they wouldn't want to be without, especially for air warning, there was likely a degree of frustration and perhaps apprehension about its limitations in surface actions or against submarines. They were fighting skilled enemies who excelled at night combat, and their electronic eyes sometimes felt like fuzzy glimpses than crystal clear vision. This operational reality, the gap between the promise of radar and its actual performance in the chaotic conditions of naval warfare, likely reinforced the Axis perception. They saw the limitations because the limitations were real. What they couldn't see, was the revolution about to make those limitations obsolete. It wasn't an American invention initially, but a desperate gift from an ally fighting for its very survival. The story of centimetric radar, the technology that would transform Allied capabilities and silence Axis mockery, has its roots not in America, but across the Atlantic in Great Britain. Facing the imminent threat of German invasion and already locked in a life-and-death struggle in the air and at sea, British scientists were pushing the boundaries of technology with incredible urgency. They too understood the limitations of meter wave radar. While chain home was vital, they desperately needed radar systems small enough and precise enough to fit into night fighters to intercept German bombers, and effective enough to hunt U-boats from aircraft and escort ships. They knew shorter wavelengths were the key. The challenge was generating powerful radio waves at these incredibly high frequencies, billions of cycles per second, corresponding to wavelengths of just a few centimeters. Existing vacuum tube technology just couldn't do it efficiently. Power dropped off dramatically as frequency increased. Then in early 1940, two scientists at the University of Birmingham, John Randall and Harry Boot, working under the guidance of Professor Oliphant, had a breakthrough. They developed a device called the resonant cavity magnetron. It was, frankly, revolutionary. Using a clever arrangement of resonant cavities within a copper block and a powerful magnetic field, their device could generate pulses of microwave energy, initially at a wavelength of about 10 centimeters or 3 gigahertz, with unprecedented power levels, kilowatts, where previous microwave generators produced mere watts. This was the missing piece, the technological
call leap needed to unlock the potential of microwave radar. It was small, relatively simple to manufacture once the design was perfected, and incredibly powerful for its size. The potential was immediately recognized. A 10-centimeter radar could use small, easily steerable dish antennas, produce a beam narrow enough for precise targeting and high resolution, and crucially, it would be far more effective at detecting small targets like periscopes and low-flying aircraft, while also suffering less from sea clutter. But Britain in 1940 was stretched to its absolute limit. While they began incorporating the magnetron into their own radar designs, they lacked the industrial capacity to mass-produce the device and the radar sets quickly enough, especially while fighting off the Luftwaffe and trying to keep the Atlantic supply lines open. They needed help. Enter the Tizard Mission. In the summer of 1940, with the Battle of Britain raging, a delegation of top British scientists led by Sir Henry Tizard embarked on a secret mission to the United States. Their goal was audacious: to share Britain's most advanced military technologies, including secrets like the jet engine and vital research on atomic energy, with the still neutral Americans in the hope of securing U.S. industrial and scientific assistance. Among the treasures they brought was the cavity magnetron, specifically Magnetron number 12. When American scientists at the newly formed National Defense Research Committee, NDRC, particularly those at the specialist laboratory set up at Tuxedo Park, New York, were shown the British magnetron in September 1940, they were stunned. I. Raby, a future Nobel laureate who was present, later called it the most valuable cargo ever brought to our shores. The Americans immediately grasped its significance. They had been struggling with the same microwave power generation problems. The British device was orders of magnitude more powerful than anything they had achieved. It was the key. This sharing of technology, born of desperation on Britain's part, was a pivotal moment. It kick-started an unprecedented collaboration and a technological race within the war. The NDRC, under Vannevar Bush, moved with incredible speed. Recognizing the potential of microwave radar, they established a dedicated laboratory at the Massachusetts Institute of Technology, MIT, in late 1940, the famous MIT Radiation Laboratory, or Rad Lab. Its mission? Turn the British magnetron into practical, mass-produced radar systems for American and Allied forces as quickly as humanly possible. Bell Labs was also brought in to refine and mass-produce the magnetron itself. The Rad Lab became the epicenter of microwave radar development, attracting some of the brightest physicists and engineers in the country. It was, in many ways, the radar equivalent of the Manhattan Project, a massive, top-secret, high-priority effort to harness a new technology for military advantage. They didn't just copy the British designs, they improved upon them, developed new components, designed complete systems for air, sea, and ground use, and established the theoretical and practical foundations of microwave engineering. The atmosphere was electric, driven by the urgency of the war. Within months, prototypes were being tested. The contrast between this hidden, frantic development in microwave technology and the operational reality of meter wave radar at sea couldn't have been starker. While Axis observers were perhaps rightfully dismissing the performance of early U.S. meter wave sets, behind the scenes, a technological tidal wave was building, powered by that small British invention and the immense industrial and scientific might of the United States, now fully mobilized for war. The mockery wouldn't last much longer. The establishment of the MIT Radiation Laboratory in late 1940 marked the beginning of an astonishingly rapid and transformative period in radar development. Think about the pressure. The war was escalating, the U-boat threat was critical, and the vast distances of the Pacific Theater demanded superior detection capabilities. The Rad Lab wasn't just tweaking existing designs, they were essentially inventing a whole new field of microwave engineering on the fly, while simultaneously designing, building, and helping to deploy operational radar sets for American and Allied forces as quickly as humanly possible. Bell Labs was also brought in to refine and mass-produce the magnetron itself. The Rad Lab became the epicenter of microwave radar development, attracting some of the brightest physicists and engineers in the country. It was, in many ways, the radar equivalent of the Manhattan Project, a massive, top-secret, high-priority effort to harness a new technology for military advantage. They didn't just copy the British designs, they improved upon them, developed new components, designed complete systems for air, sea, and ground use, and established the theoretical and practical foundations of microwave engineering. The atmosphere was electric, driven by the urgency of the war. Within months, prototypes were being tested. The contrast between this hidden, frantic development in microwave technology and the operational reality of meter wave radar at sea couldn't have been starker. While Axis observers were perhaps rightfully dismissing the performance of early U.S. meter wave sets, behind the scenes, a technological tidal wave was building, powered by that small British invention and the immense industrial and scientific might of the United States, now fully mobilized for war. The mockery wouldn't last much longer. The simultaneous application of centimeter radar to the U-boat problem was just as transformative. The Rad Lab and its collaborators were tackling this problem with microwave airborne radar. The ASG radar, also operating at 10 centimeters, could be fitted into patrol bombers like the B-24 Liberator. Its ability to detect small targets like submarine conning towers or snorkels, even in heavy seas that blinded older meter-wave ASV sets, was a game-changer in the Battle of the Atlantic. Combined with improved depth charges, code-breaking intelligence from ultra and long-range aircraft, Centimeter ASV radar allowed Allied planes to effectively hunt U-boats day and night in almost any weather. U-boat crews, previously relatively safe on the surface at night, found themselves under constant threat. Their radar warning receivers, designed for meter wave frequencies, initially gave no warning of the approaching microwave radar-equipped aircraft. Losses mounted catastrophically for the German U-boat arm in mid-1943, a period known as Black May, forcing them to temporarily withdraw from the North Atlantic. Admiral Donitz, head of the U-boat force, acknowledged the devastating impact, attributing the reversal primarily to Allied radar advances. Beyond surface search and anti-submarine warfare, Centimeter radar found countless other applications. Higher frequency X-band radars, 3 centimeters, were developed, offering even better resolution, ideal for airborne bombing radars like the H-2X Mickey set used by bombers, and shipboard fire control systems like the Mark 8 radar used with main battery directors. These fire control radars could lock onto a specific target and provide continuous, highly accurate range and bearing data directly to the ship's gunnery computers, allowing for effective blind fire even against maneuvering targets. Smaller, simpler microwave sets were developed for PT boats and landing craft. The pace of innovation was relentless. New techniques like lobe switching and conical scanning improved tracking accuracy. Countermeasures and countermeasures became a constant back-and-forth technological battle. The scale of the effort was immense. By the end of the war, the Rad Lab had overseen the development of over 100 different radar systems, and American industry had produced millions of magnetrons and hundreds of thousands of radar sets. It truly was a Manhattan Project-level effort, though its secrecy meant its full impact wasn't widely appreciated until after the war. The initial Axis mockery, based on the real limitations of early meter-wave radar, had become tragically ironic. While they were still refining their existing technology, the Allies, jump-started by the British Magnetron and powered by American industrial and scientific might, had leaped generations ahead in radar capability. Those few centimeters in wavelength had translated into a decisive strategic advantage on the high seas.
So how did the Axis powers react when they started encountering this unexpectedly effective new Allied radar? The shift wasn't instantaneous, of course. Military technology adoption takes time, and intelligence gathering in wartime is fraught with difficulty and uncertainty. But by 1943, the evidence was becoming undeniable, particularly for the Germans in the Atlantic and the Japanese in the Pacific night battles. For the German U-boat crews, the appearance of Allied aircraft, seemingly out of nowhere, especially at night or in bad weather, was terrifying and baffling. Their existing METOX radar warning receivers, designed to detect the longer wavelengths of the older British ASV Mark II radar, were silent against the new 10-centimeter microwave sets. They were being blindsided. German intelligence eventually captured downed Allied aircraft equipped with the new radar, like the H-2S bombing radar, including intact cavity magnetrons. This was a shock. They realized the Allies had made a massive technological leap they hadn't anticipated. Their response was twofold: develop countermeasures and try to catch up technologically. They rushed development of new radar warning receivers capable of detecting centimetric waves, like the Naxos and Tunis systems. These provided some warning, but were often unreliable or had limited range. They also experimented with radar-absorbent coatings, codenamed Sumpf and Schornsteinfeger, for snorkels and conning towers, trying to reduce their radar cross-section, with limited success. Technologically, they tried to accelerate their own microwave radar development, creating systems like the 9-centimeter Berlin airborne radar and the 3-centimeter Rotterdam device, both based heavily on captured Allied tech. But these came too late,
and in too few numbers to significantly impact the outcome of the U-boat war. The damage had been done. The technological advantage gained by Allied centimetric radar in the Battle of the Atlantic proved decisive. The story was similar, though perhaps unfolded a bit more slowly, in the Pacific. The Japanese Navy, initially confident in their night-fighting prowess, began suffering increasingly heavy and inexplicable losses in night surface engagements starting in late 1942 and accelerating through 1943. Battles like Cape St. George starkly demonstrated the effectiveness of American SG radar-directed torpedo and gun attacks. Japanese sailors reported being accurately targeted by enemy gunfire, even when visual contact was impossible due to darkness or smoke. While the Japanese did develop their own radar systems throughout the war, including some later models operating in the decimeter and even centimeter ranges, like the Type 22 surface search radar, around 10 centimeters, their development and deployment lagged significantly behind the Americans. Their industrial capacity was limited, quality control could be inconsistent, and integrating radar effectively into fire control systems and fleet doctrine proved challenging. They captured some Allied radar equipment, but struggled to replicate or counter it effectively on a large scale. There was a sense, reflected in post-war analyses, that the Japanese military leadership perhaps didn't fully grasp the revolutionary impact of microwave radar as quickly as the Allies did, still placing significant faith in traditional methods until relatively late in the war. The initial dismissal, born from observing the limitations of early meter wave sets, had perhaps created a mindset that was slow to adapt when the technological landscape fundamentally shifted. They were caught off guard by the sheer speed and scale of American radar development, fueled by the cavity magnetron. The mockery turned to grim reality as Allied ships and aircraft, equipped with these superior electronic eyes, gained increasing dominance in detection, targeting, and situational awareness, contributing significantly to the eventual Allied victory in both the Atlantic and the Pacific. The useless toys had become indispensable weapons. The story of centimetric radar in World War II is more than just a tale of technological advancement. It carries some important lessons that resonate even today. Firstly, it's a powerful reminder of the danger of underestimating an adversary, especially in the realm of technology. The Axis powers, particularly Germany, had capable scientists and engineers. Their initial assessment of meter wave radar's limitations wasn't entirely wrong based on the physics they understood and the technology they possessed. However, their mistake was assuming that their understanding represented the ultimate limit, failing to anticipate the possibility of a disruptive breakthrough like the cavity magnetron. This kind of technological surprise can rapidly shift the balance of power, and complacency or arrogance based on current superiority can be fatal. History is littered with examples of established powers being overtaken by those who embraced innovation more readily. Secondly, the story highlights the incredible impact of international scientific collaboration. The Tizard Mission, where Britain shared its crown jewels of technology, including the magnetron, with the U.S., was a strategic masterstroke born of necessity. It combined British ingenuity with American industrial capacity to create a capability far greater than either nation could likely have achieved alone in the same time frame. This pooling of knowledge and resources, even between allies who sometimes had competing interests, proved immensely powerful. It underscores the idea that progress often accelerates most rapidly when information and expertise are shared rather than hoarded. Thirdly, the rapid development and deployment of over 100 distinct radar systems by the MIT Rad Lab in just 5 years is a testament to what can be achieved when scientific talent, adequate funding, and a clear, urgent mission converge. It shows the power of focused, large-scale research and development efforts in wartime, but also holds lessons for tackling major challenges in peacetime, whether in science, medicine, or other fields. When the stakes are high and the goal is clear, remarkable progress is possible. Finally, the evolution of radar during the war demonstrates the constant cat-and-mouse game of military technology. The initial advantage gained by centimetric radar was eventually countered by Axis development of warning receivers and later their own microwave systems.
This cycle of measure, countermeasure, and counter-countermeasure continues to this day in electronic warfare and other military domains. Maintaining a technological edge requires continuous innovation and adaptation, as any advantage is likely to be temporary. The radar duel of World War II fundamentally changed naval warfare, diminishing the importance of visual spotting and night fighting skills that had dominated for centuries and ushering in an era where electronic sensors became paramount. It saved countless Allied lives and played a significant role in victory. The legacy of the cavity magnetron and the work done at the Rad Lab extends far beyond the war. It laid the foundation for modern microwave technology, impacting everything from air traffic control and weather forecasting to the microwave in your kitchen. That initial Axis mockery, therefore, serves as a fascinating historical marker, a moment of misplaced confidence just before a technological tide turned, reminding us that in warfare, as in so many things, what you don't know or what you refuse to believe is possible can often hurt you the most. It's a lesson about humility in the face of innovation, a lesson paid dearly on the battlefields of the sea. We've covered a lot of ground, tracing the story from early radar limitations to the game-changing impact of centimetric waves. It's a complex topic, but hopefully breaking it down step by step has made it clearer why the Axis powers initially felt confident in dismissing early American systems. They simply didn't foresee the technological leap that was coming. We explore more incredible wartime innovations in this playlist here. Click over to keep learning about the ingenuity that shaped our world. We hope this story sheds some new light on a crucial part of naval history. For more stories from that era, check out the videos we've linked on your screen. Thanks for joining us on this journey back in time.